Sheldon Joyner of Brandeis University. We'll be talking about a shuffle product formula for generalized iterated intervals.
Thank you. So thank you very much to the organizers for the opportunity to be here. It's a great conference. So I'm going to begin by establishing some notation. This is not on. And the starting point is this iterated interval expression for the Riemann zeta function. So of course, here these z's they are n different z's, but it's convenient to me to use the same letter for all of them, and you'll see why in a moment. We can generalize this in a couple of ways. First of all, let me just point out that my convention is to integrate from left to right. Now, the first way that we could generalize this is to consider multiple versions. Okay, so these are the usual multiple zeta values. And the second way that we could generalize these is to change the path of integration. So instead of integrating, what did I call n? Instead of integrating from 0 to 1, which incidentally, I'm thinking of this as a tangential path in P1 minus 3 points between 0 and 1. So instead of this, we could integrate from 0 to z, where z is some point in the unit disk, and that's the only change we make. So here, dt over 1 minus t. And similarly for the multiple polylogarithms, so these are the polylogarithms, and we get multiple polylogarithms by making a similar change here. So if we change this to t, then this would be the multiple polylogarithm corresponding to this tuple of integers. Okay. So here's a third way that we could think about generalizing these expressions. And let's go back to the very first one. This works for integers, right? So this is n, that's an integer greater than 1. And we might ask the rather quirky question, could we make sense of this if we replaced n by some complex number? And the answer is yes. So here's how we're going to do this. So first of all, we will exploit the two properties. Firstly, the antipode property. And secondly, the shuffle product formula in the following form. So if you repeat the same form n times, then this is the same as 1 over n factorial times the n-fold product of this. So on the left-hand side, this is the integral over the simplex, whereas on the right-hand side, this is just a product of integrals over the line, over the interval. Okay, so using these two ideas, we're going to generalize iterated integrals in the following context. M will be some Riemannian surface. And let's say alpha and beta will be polymorphic one forms. And let's say that gamma is some path with suitable smoothness on M. So the gadget we'd like to define is an iterated integral of the form alpha beta to the s over gamma. And we define it as negative the integral over the reverse path. First of all, integrate beta along this reverse path, starting at the beginning point of gamma to some parameter z. So this notation means integrate along gamma to the parameter z, where z is just some parameter gamma inverse. And we want to divide this by gamma s plus 1. So the nice thing about the second formula, the shuffle product formula, is that we know how to generalize this because n factorial generalizes using the zeta, the gamma function. And then alpha, and here this alpha is now going to be integrated over the parameter z. It's just a line integral. Okay. Now, with this setup, we can, well, first of all, I should point out that if M is the thrice punctured sphere, which will actually be the case of greatest interest, because then we're going to be dealing with poly-zeta functions, then these integrals are actually nothing other than the Riemann-Liouville fractional integrals. So this coincides with Riemann-Liouville fractional integrals. Under the usual change of coordinates to the complex plane. But of course, having this iterated integral perspective gives us a lot of new information and a new way of seeing things. So the first thing to note is that we have an iterativity property. And the first few things I'll mention will hold in for general surfaces, not just P1 minus 3 points. So the iterativity property looks like this. And I forgot to mention this as well. Of course, this is for complex numbers S for which everything converges. So it must make sense for it. So this is the same as alpha beta to the n, where here this is regarded in the usual sense of just integrating iteratively, beta to the s minus n, provided everything converges. So one can check that these really are iterated integrals in this sense. And the second property of that we can generalize is that of the coproduct formula. So as you know, in the classical case, we do have a coproduct formula for iterated integrals, and maybe I should write it down. So if you integrate over successive paths which can be concatenated, then this is the same as first integrating a certain number of them, which could be 0, in which case the coefficient is just 1. J goes from 0 to r, multiplied by the integral over the second path. And again here, if j equals r, then the second factor is interpreted as being 1. So this generalizes to this setting. Again, subject to the proviso that everything converges. We have the following formula. The integral over delta of alpha beta to the s plus a sum of all non-negative integers alpha beta to the n times the integral of beta to the s minus n. So this is the coproduct formula that works in this case. The proof is very elementary, using some basic differential geometry. And I should say what I mean by this when this doesn't converge. So if the real part of s is too small, then this won't make sense. And so we interpret it as s choose n the integral of beta to the s over the integral of beta to the n. So really this is just suggestive notation to sort of mimic what's happening in the usual classical case. But really this is what we mean in case this doesn't converge. Or in fact, right, so when the real part of s minus n is negative in the p1 minus 3 points case, then this is how we have to interpret these. When beta is going to be dz over z. Okay. Beg your pardon?
Why does it converge after that?
Well, I mean, this thing.
The infinite sum.
Infinite sum. Oh, the infinite sum. So this just comes from the binomial formula. I must say that there are some convergence conditions which must be satisfied. Yes. So for example, here one needs something like this. The integral of beta along delta has to exceed the integral of beta along gamma. No, delta. Has to exceed the integral along gamma up to any parameter z in order for convergence to occur. And then there's also some other conditions so that we can use Lebesgue-dominated convergence. So there are some convergence issues that we have to deal with here. But there are a couple of interesting features of this formula. The first is that for integers, so remarks. Firstly, notice that if s is an integer, the formula works automatically. It works as is. And the reason for this is that these binomial coefficients are 0 if s is exceeded by n. And the second thing is, well, this formula is much simpler than you might expect, actually. Because the only thing that can, it's as if the only thing that can shift over are integers, integer powers of beta. You see, if you look at this formula in the classical case, you might expect that somehow you have to be able to shift beta to the s across the integral, but you only have to shift integers. And so that's kind of the guiding philosophy for where the shuffle product formula will come from. So we only have to shift. I know this is rather a vague statement, but hopefully you can understand what I mean. We only have to shift by integers between the two respective integrals over the respective paths. Okay. So next, what we'll do is to consider the shuffle product formula. So if m and l are some integers greater than 1, then the cases of interest in the classical situation look like this. So throughout you should think of alpha as being like dz over 1 minus c and beta like dz over z over some path in p1 minus 3 points. So we have some polylogarithm or multiple zeta value. Then if we consider a path gamma and integrate alpha beta to the m and multiply this by well, let's say multiply this by eta beta to the L. And of course there are multiple versions of this, so I don't want to obscure things by writing down such expressions. But the way that the shuffle product formula works, as you know, it's as if you were shuffling two halves of a deck of cards, and the respective orders of the forms and the two integrals have to be preserved. So what we'll end up with here is L plus n choose n when we shuffle n of the betas past eta and then intersperse these amongst the L plus n betas which result. You have L plus n choose n possible choices of position of beta amongst of the n betas amongst these. Alpha beta to the m minus n, eta beta to the L plus n. And here n goes from 0 to m. And then the reverse when the eta comes first. So plus so eta beta to the L minus n alpha beta to the m plus n. Okay. So this is it'll prove to be useful to think about the shuffle product in this way, to see where the shuffle product formula will come from in the general case. Okay, so next, what I'm going to be talking about entirely is this case of P1 minus 3 points. So it's fortunate that this is an interesting case, because it turns out to be much easier, and things work rather nicely. So what we're going to do in this case, we can frame things very generally. Let's say that alpha is of the form fz dz, where f of z is analytic in a neighborhood of 0, and it vanishes at 0. So power series starts at 1, and here we want the coefficients to be big O of n to the c1, say, where c1 is some positive quantity. And similarly, eta will be gz dz with similar properties, so some analytic thing in the neighborhood of 0. That vanishes at 0, and the coefficients are big O of n to the c2. So under these hypotheses, then the integral, sorry, I ought to have said what beta is. Beta will be dz over z. So under these hypotheses, alpha beta to the s along gamma, this converges if the real part of s exceeds c1 plus 1. Okay, so here is a proposition. This is working in the P1 minus 3 points case. So with alpha, beta, and eta as above, and gamma will be some path in P1 minus 3 points. So the paths of interest will emanate from 0 to some point z in the unit disk. Then the shuffle product formula looks like this. Alpha beta to the s along gamma times eta beta to the t along the same path. This is the sum of t plus n choose n multiplied by the integral along gamma of alpha beta to the s minus n eta beta to the t plus n. And we sum over all non-negative integers. So again, looking at the coproduct formula, the only thing that's shifting is the only thing that are shifting are integer powers of beta can be shifted across eta, and then you have to just count, as it were, how these extra things can be placed amongst the t plus n things that arise. Okay. So there are various other forms of this. I'll write down in a moment. There are multiple versions of this thing, this expression. So let me just quickly state how the proof goes. The proof is very easy. So the first part of the proof involves the following case. So let's take alpha to be za dz over z. dz over z. And then what we have to compare is on the left-hand side, we have z to the a plus b over a to the s plus 1 a plus b, sorry, b to the t plus 1. And I forgot to mention where this converges. So this converges for the real part of s greater than c1 plus 1 and the real part of t greater than c2 plus 1. So this is what we get on the left-hand side, and we have to compare to, on the right-hand side, when you make this calculation, you get z to the a plus b over a to the s plus 1 a plus b to the t plus 1 multiplied by the series. Let's see. So here you're going to get an a to the n and an a plus b to the n. Okay, so now you can just use some elementary techniques using this formula for the binomial expressions. And this series is exactly the stuff you need to cancel out the extra term. So this is going to be a plus b over b to the t plus 1. The second part is much more technical, and I'm not going to write this down, but this involves convergence issues. So the second part, I should have said sketch of proof. Okay, now something rather curious happens. This formula does not converge if both s and t are integers. So this is s and t not both integers. So for the convergence, you have to basically use Lebesgue-dominated convergence theorem. And in the integer case, roughly speaking, the idea that the reason that it fails, it has to do with the fact that the poly-zeta functions, so these are defined as the following things. So these things have poles on certain hyperplanes. SR equals 1 and the real part of, no, not the real part. SR plus SR minus j plus 1 equals j minus n for j greater than or equal to 2 and s equal to r and n greater than or equal to 0. Okay, so this is the reason that this is going to fail in the integer case, because of these poles. Okay, so coming back to the classical case, so we have this coproduct formula, we have a shuffle product formula, and we have an antipode property. So we've seen that all of these things hold in this generalized situation. I didn't tell you how to do this for more than 2 indices, because the formulas just become very unwieldy. But these coalesce in the structure of Hopf algebra in both situations. So we have to be a little careful about the antipode property in this case. Perhaps before I do that, let me write down a couple other versions of this shuffle product formula. It's really not clear on the face of it that this thing should be commutative, right? But it is certainly commutative. I mean, the expression as it stands doesn't look commutative, but obviously multiplication of these numbers is commutative. But here's a symmetric version from which this is more apparent. So in fact, maybe I should just write down the multiple version of this. So let's say we have alpha beta 1 to the S1 through alpha r beta to the SR times eta 1 beta to the T1 through eta u beta to the TU. Well, in this case, one can write down a similar formula to that. I'm not going to do this. I'm instead going to just write down the symmetric form. So what happens here is that the only stuff that can get shuffled in amongst the second lot of integrals are integer powers of beta. And so the forms of the integrals that arise are going to look like this. So let's say that SR is not an integer. So minus some sum of integers in I, where I goes from 1 through to u. And these copies of beta that get split off here get distributed amongst these betas. So eta 1 beta to the T1 plus N1, and so on. And again, there's some binomial coefficients. So T1 plus N1, choose N1. And in the symmetric form, one just has to subtract 1 from the last coefficient. So then you have the same thing repeated with the opposite order. So here you have the etas first. Exactly the same kind of thing. So this a similar formula. Maybe I should just not be lazy and write it down. And one sums over all possible tuples. Okay, so that's the symmetric form from which it's evident that these are commutative. Associativity of the product is not immediate, but it also holds. So associativity, this follows from first of all, it follows from the fact that you're multiplying complex numbers. So it has to be associative. But it also follows from some identities involving binomial coefficients. Okay, so in order to think about this Hopf algebra structure, we should formalize the setup. And so we'll introduce some formal variables x0 and x1, as well as x0 to appropriate complex powers. And if you like, you can think of this as exponential of s log x0. So then words, we'll have admissible words in these variables. Will correspond to integrals in an obvious way. So if you have some integral. So now we want to think specifically of poly-zeta functions. So So something like this will correspond to the word x1, x0 to the s1 minus 1, and so on. Okay. The difficulty with the antipode property is that the regularization procedure is unclear. So if you want to allow an antipode property, then you need to, so the antipode property says this. If you reverse the order of integration, then you reverse the order of in which the forms appear, and you pick up a factor of -1 inside each of these parentheses. But the problem is that the word codifying such an integral will not be in this algebra. So that's a problem when it comes to allowing the antipode. But at any rate, we do get a bi-algebra suitably interpreted. So let's just look at this bi-algebra structure. First of all, the first thing to note is that the coproduct formula for generalized iterated integrals is not symmetric in the sense that you would like. So remember that if we have something like alpha beta to the s, then we get a sum of this form. So again, I'm sweeping the convergence issue under the rug, but there's some conditions which have to be satisfied here. So this is alpha beta to the n over gamma times beta to the s minus n over delta. And the reason here that the s doesn't occur in the gamma integral, the integral over gamma, has to do with these convergence issues. So consider this versus alpha beta to the s minus n times beta to the n. So this is correct, and the second one is not correct because of convergence issues. But unfortunately, the way that this product interacts with the shuffle product formula, one needs to have both of these things on the same footing. So we'll define, first of all, let's define A to be all C linear combinations of these admissible words. And then we define a coproduct in the usual way from A to A tensor A by taking some word like x1, x0 to the s and mapping it to 1 tensor x1, x0 to the s plus the sum x1, x0 to the n tensor x0 to the s minus n. So it's the usual thing. This is just patterned on this integral expression, right? Okay. And as I said, this doesn't work when you just consider this formalization of this co-product together with the shuffle product formula. So we have to impose some relations. We have to say that this is equal to the thing that you get when you allow S on this side. So plus.
Excuse me, what do you mean admissible words?
Admissible words are going to be the ones for which the integral converges. Basically, if it has this structure.
S is a complex number.
What's a complex
S
number?
is a complex number. S1.
These are complex numbers, right?
Admissible word.
Yes.
And do you include just the unit, the one?
What do you mean? Oh, 1, yes.
Okay.
Yes, and 1.
Oh,
And 1.
this linear combination is just a finite linear combination.
Finite limit. No, not finite linear combinations, because we want to take infinite. We want to take infinite things. Right.
And S is a complex number.
S is a complex number. Yes.
And you consider infinite number.
I allow different values of S. Yeah. As long as so I allow anything for which the corresponding integral makes sense. When I interpret this as dz over z, 1 minus z, and dz over z. Does that make sense? So they have to satisfy this integral has to converge, right? That's all. Okay. So here we impose some condition like this. And the second thing that we have to do is actually impose the suitable commutativity relations, because there's a problem when it comes to products which have different complex powers. So for example, if you take a product what letter can I use here? Theta beta to the U. So if you work this out, this must be the same thing as theta beta to the U times the other stuff. However, the words that appear on this side will have this form: x1 x0 to the s minus n1 minus n2, and then x. So there's going to be some double sum here. Actually, a triple sum, I guess. And then here you'd have t minus m plus n1 and u plus m plus n2. Right? Once you carry out this procedure, this multiplication, firstly multiplying these two together and then this one, this is what you get on the left-hand side with some coefficients. Versus on the other side, the u is going to be in this position. So the only way that these things will actually match formally is if you impose these relations on your algebra. So because formally there's no reason for something with x0 x1 x0 to the u minus something to equal x1 x0 to the s minus something when s and u are different complex numbers. So over here you have some coefficients: x1 x0 to the u minus n1 minus n2, x0 to the s minus m plus n1 to the t plus m plus n2. And so really there's no way that these are going to match up formally unless you say this. So you impose these commutativity relations. Okay, and under these assumptions, we can say the following. So the co-product from A to A tends to A is an algebra homomorphism. So we have a co-algebra structure. Okay. So I have a little time to. I hope that you will. Well, you have no choice, I guess, to indulge me some amusing formulas. So I'm gonna make a definition. So x will be some tuple of functions from z to c. So these could be characters, but they could also be some other functions. So the xj are maps from z to c. So these could be Dirichlet characters. Or some other functions, and we'll see examples just now. M underlined will be an r minus one tuple of integers. And then we'll define, or let's just introduce some notation. S underlined will be S1 through SR. These are complex numbers. And now we define the following thing. Zeta of S bar M bar X. So this is chi1 of N1, chi2 of N2 minus N1 through chi R of N R minus the sum of the other n's. R minus 1. This is a sum over integers n1 greater than 0 and less than n2 and so on. So what I'm writing down are the kinds of things that show up naturally on the right-hand side of our shuffle product formula. And then multiplied by n1 over n2 to the m1 through nr minus 1 over nr to the mr minus 1. So let's call these tempered, or let's say mx tempered polyzeta functions. And it's rather amusing that we can express various things in terms of such things. The first example is if you have an abelian number field. So suppose K over Q is abelian, a finite extension. Well, then as we know, the Dedekind zeta function can be factored as the product of all the L functions corresponding to characters of the field. Okay, now these L functions can actually be expressed as generalized iterated integrals as well. So these are iterated integrals over the character applied to A times z to the A, where A runs from 1 through F, where F is the conductor of the character, 1 minus z to the F, dz over z times dz over z to the S minus 1. So L functions have iterated integral expressions. And now the shuffle product formula enables us to express this product as a sum of tempered polyzeta functions. So using I'm not going to write down this formula. Using the shuffle product formula, I can't think of any good reason that one would like to do this, but we can. So if you don't like products, maybe if you only like sums, using the shuffle product formula, we can express the Dedekind zeta function as a sum of tempered polyzeta functions. In fact, you can also express the Riemann zeta function itself as a sum of tempered polyzeta functions. So the 1 over zeta s, as we know, is the Möbius function at n over n to the s. This is easy to prove from the product formula, Euler's product formula. So 1 is the same as the product of zeta and 1 over zeta. And so this is actually the same as s plus n minus 1, choose n, zeta s n, and I'm using this notation, mu, and 1 will be the trivial character. So one has this kind of thing. You could also do this with, what are the other examples I have? So zeta s divided by zeta 2s. So there's a whole slew of formulas of this kind. I'm not going to write down all of the ones that I have. So there's the first, and here's the second. So zeta s itself is zeta 2s times zeta s over zeta 2s. And so again, using this idea, you get a sum of these tempered polyzeta functions. And I'm going to finish earlier than anticipated, but I'll probably take 5 minutes to give a multiple zeta value proof of the prime number theorem. So here's a lemma. The lemma says that zeta s being 0 free on the real part of s equal to 1 implies the prime number theorem. Okay, so this is not so hard, and you can look it up at any classical number theory book. So let's prove that zeta s is 0 free on the line real part of s equal to 1. So let's think about zeta of 1 plus it. So at zeta of 1 plus it, t is some real thing that's not 0. So at such a point, the zeta function is analytic. So I should just say at 1 plus it. Zeta is analytic. So if it vanishes, well, it has some power series expression, so it has to vanish to order greater than or equal to 1. So let's suppose that we have such a point. So suppose zeta of 1 plus it equals 0 for some t other than 0. And then let's consider for a positive epsilon, zeta of 1 plus epsilon times zeta of 1 plus it plus epsilon. we can use the shuffle product formula, and we can so this gets expressed as a sum of 1 plus it. Do I have to minus 1 here? Minus 1 plus epsilon, choose n, and then we have, actually I want to do this the other way around, sorry. So 1 plus epsilon minus n, choose n, minus 1. And then here I'll have zeta of 1 plus it plus epsilon minus n, and 1 plus epsilon plus n. Okay. N greater than equal to 0. So assuming that this thing is 0, we know that it vanishes at least to order 1. And so if we take the limit of the left on the left-hand side as epsilon goes to 0 from the right-hand side, then this must converge to some finite quantity. So this converges to some kappa, which is finite necessarily, because we know that zeta has a simple pole at s equals 1. Whereas on the right-hand side, all we have to do is consider the n equals 0 term. For the n equals 0 term, we have this thing, 1 plus it plus epsilon and 1 plus epsilon. And as epsilon goes to 0, this thing blows up. So remember, I'm using the opposite notation to everybody else. So this means 1 over m to the 1 plus it, n to the 1, sorry, plus epsilon, 1 plus epsilon, and m is less than n. Okay, so as epsilon goes to 0, you land up on this hyperplane where there's a pole of this polyzeta function. So this thing explodes as epsilon goes to 0. And that's a problem. So this shows that there is no such point. So that's where I'll stop. Thank you.
Sorry, I just missed the last point because I'm a long way away. You said the left-hand side is finite, and there are
And the limit as epsilon goes to 0. Yes.
and the right-hand side contains one infinite term. Why couldn't that infinity be cancelled by some other term that I can't see?
Because these other terms are finite.
The other terms are finite. That was the term I was missing.
Yeah.
There's a unique infinite term.
Yeah, because the poles of the polyzeta function are these tuples of integers. These things are going to be integers greater than 1.
Okay.
So it won't happen again. Yeah.
Okay. No one has any other questions? Let's thank the speaker again.
Thank you.